We're going to take a look at section 5.1 on approximating the area under curves. And we have talked a lot about applications for differentiation, such as the slope of a tangent line, but now we need to talk about some applications for integration. So if we have a function f of x, we can both differentiate it and integrate it. The derivative, we've got lots of applications before. Slope of tangent lines is just one of them. And then the integral, we haven't gotten into any of those applications yet. So it's going to be our discussion for the rest of this chapter. So it's going to take us a couple of different sections to fully develop the concept, but we're going to be working on those applications of integration. All right. So on our next page, we're looking at example 1. We want to consider this velocity function for an object, and then I'm going to describe the motion of the object over the interval. Okay, so we have to keep in mind that this is a graph of velocity, not of position. So if velocity has a negative slope, that means that it's not talking about the position going down, it's talking about the velocity going down. So that means that the velocity or speed is decreasing. Okay, so that means that over the interval from 0 to 1, the velocity, it's positive. I mean, it's still a positive value. It's above the x-axis. It's just decreasing. It's becoming a smaller positive value. So the velocity is decreasing. And then on the interval from 1 to 3, the velocity is going to stay the same, so it's constant. So the velocity is constant. We can even be a little more specific. It is specifically, I don't know the units, meters per second. So it is specifically 10 meters per second. Okay. Then on the interval 3 to 4, the velocity is increasing. Now we can be even more specific. We can say it's increasing from 10 meters per second to 30 meters per second. And then we can say that on the interval 4 to 6, the velocity is constant again. I don't have any more space, but I can push this up. The velocity is constant specifically at 30 meters per second. Okay, so those are things I know about the velocity graph, about where it is decreasing, where it is increasing. What I want to do is figure out what this means about the position. So first of all, we want to use geometry to find the area between the velocity function and the t-axis. This is the t-axis for the interval 0 to 3. And how can this value be interpreted? Okay, so I want to go 0 to 3. And so the area between the velocity and the t-axis would be the area of these regions. Okay, so I have this interesting shape right here. It's like a trapezoid and a rectangle, but I'm actually going to divide it just into a triangle and a rectangle because that's going to make it easier for me to use geometry to find the area. So for the triangle part of it, we're going to have 1/2. The base of the triangle is 1, and the height of the triangle from 10 to 20 is 10. Then for the rectangle part of it, we have the base of the whole rectangle is 3, and the height of the rectangle is 10. So that's going to end up with an area of 35. Now, the units on this, since I'm multiplying a time in seconds value on the length or base by a meters per second value, if I multiply meters per second by second, this is going to be in meters. Okay, so the units on this are in meters. So the area here gives me a distance, right? So this gives me some kind of distance traveled over that time. Okay, so over 3 seconds because it was on the interval 0 to 3. All right, So we can just calculate this. We know that we started off going at a speed of 20 meters per second, and we decreased to a speed of 10 meters per second over 1 second. Then we maintained, if I look at just this part of it, we maintained a speed of 10 meters per second for the next 2 seconds. So I know that for that's the 20, and then it seems like I must have traveled another 15 in that one. Might have made sense to separate them this way, but I thought it was easier to do the area of a triangle and a rectangle versus a trapezoid and a rectangle. So total distance traveled is 3 in 3 seconds was 35 meters. That's one of the applications of area under a curve. Okay, so recall from section 3.6 that displacement is equal to final position minus initial displacement if the velocity function is always positive, which it's not, but this case it was. If the velocity function is always positive, then distance and displacement are going to be the same. So I did use the word distance up here. I need to be careful with that word because we're usually talking about displacement, not distance. So we are going to be trying to make sure we're distinguished between these two words. Usually it's the displacement. It's only also distance if your velocity function is all positive, all above the x-axis, which it was in this case. Sometimes you want to find distance anyway, and then you're going to have to do some absolute values of graphs to make sure that you're looking at a positive function only. Okay, so a lot of times area under a curve will give us displacement. All right, so basic geometry was helpful. We can use basic geometry to find some areas. So rectangles, of course, triangles, even parallelograms, hexagons, polygons, although it's not really worth our time to do most of these. We can just cut them into triangles and do their areas. We'd like to focus on like the main couple shapes. Okay, even parallelograms sometimes will just slice into triangles as well, and rectangles, and so we'll work with those. So these all have straight lines, but most functions that you draw aren't going to have straight lines. And so how do I deal with a function that is not going to be a straight line? So method of exhaustion for creating, if I wanted to do a circle, I can create it into more and more polygon triangular sections to get the area of a circle. That's how that was first worked out. But I don't really want a geometric shape like this. I'm talking about something that's eventually going to have a velocity function that's going to be a curve. And it's not going to match with any of our known geometric objects. So we're going to need to figure out how to discuss the area under that kind of curve where I'm not made out of rectangles and triangles. Now we are going to use that method of exhaustion in a different way. Instead of cutting this into triangles, we're going to cut this shape into little rectangles. Now, each of our little rectangles will have some error in it. So we have a little bit of error right here where we're not quite correct. But the idea is that if I use enough of them, if I make enough rectangles closer and closer and closer together, the error is going to be smaller and smaller. So we're going to have some limits there, maybe as we get the number of rectangles shrinking down to with 0 there. Okay, that's a little bit of the overview of what we're looking at, and let's see how we might do that on our next page. All right, so here is a graph of a function that I want to find the area underneath it, and we can see that it has been partitioned into several rectangles. Okay, now we're going to talk about this rectangular partition up here. This is the way it's defined. So we want them to have uniform width because it makes it easier to deal with, and so we're going to first of all, if the interval goes from A to B, so we start at A and we end at B, we're going to begin with x0 at A and xn is going to be B, and then we're going to break it into n intervals. So x1 is a divider, x2 is a divider, all the way to xn minus 1. Okay. Now, because you broke it into n intervals, the length of each of these intervals is going to be delta x, which is the change in x, defined as the distance between them, b minus a, divided by n, how many intervals you wanted. So we just take the distance between the endpoints, divide by n, and that's how wide each one of them is. Okay, now, so we have the endpoints being x1, x2, x3, now, etc. We need to figure out the height of these And so we need to figure out some y values. Figuring out the x values is actually a lot easier than the y values. So I need to figure out some way to call the function. And so depending on how you draw your x value, you could have any x in the interval. So we call them x1 star, x2 star, xk star, etc. And then the y value is going to be f of x1 star or f of xk star, etc. You can just plug it into the function. Okay, and that means that the area of the rectangle, since it's length times width, length, or depending on which one you're defining length, one of the dimensions is delta x. The other one for the height of the rectangle is f of xk star. And so we can define the area of any of these rectangles as f of xk star times delta x, the height times the base. Okay, all right. So that is going to be how we begin writing down areas under curves. I'll talk about Riemann sums before I start the next one.